Okay, section 2.3, we're going to be taking a look at other set operations today. So the only set relationship, I guess, if you will, that we have discussed so far, we've discussed two of them, are complements, right? Everything outside of a set, and subsets, sets that are inside of sets. We're going to expand our ideas of that to include a lot more of the standard Venn diagrams that Ty mentioned, where the circles overlap and such like that today. So the first one we're going to look at is set intersection. So the set intersection is the set of elements that are common to both sets. I'm going to write out what that looks like notationally, and then I'm going to describe what it looks like in context as well. So the notation is an upside down U. It's an intersection. It kind of looks like a lowercase n, right? Like the without the stick part on the side. Y'all know what I'm talking about, right? Okay, yeah. So it kind of looks like that. And we write that with our set builder notation that we've been doing. This is a set of all x, such that x is in A and x is in B. The standard example I always use is of a street intersection because we drive. Most of you have driven or you've been driven by somebody recently, right? So when you drive and you're at an intersection of two streets, the intersection is the part where they cross. It's the part that's common to both streets. That's intersection. You can think about this in a relationship standpoint. If you think about your grandparents, okay? Y'all have them. Okay, so you've got your grandparents on your mom's side, and they probably have one last name, all this group of them, right? Or maybe more than one, but just pick one for the moment. And then you've got your grandparents on your dad's side, right? And you're the intersection, you're the grandchild to both sets of them. Right? So like some of my nieces and my nephews are not related to my mom's side of the family, right? They're related to my husband's family, right? So they're grandchildren for each side of the family. Okay, so that's an intersection. The set union is the set of objects that's in one set or the other or both. So the union symbol actually looks like a U. That's very friendly. And it's the set of all x such that x is in set A or x is in set B. And the understood piece that we never write down because the word or is the inclusive or is that this means or both. Okay, so it could be in both and still fit in this description. This is the family picture. Okay, so if you were having a family picture and you have blended families. So my husband came from a blended family. So his mom and his stepdad, and they have 5 kids among them all, right? So this is the family picture. We get everybody in the picture. Your kids, my kids, our kids. You saw that movie maybe? Yours, mine, and ours? Same idea. Everybody's in the family picture. Another way you can think about this is what happens when you get married, right? The preacher does not say, and now you become a joint venture. You become a union. It's a partnership, everything. So if either of you do have kids, you get the other one's kids, and now they're your kids. If one of you has debt, you get their debt too. And it's ascribed to the union of you. And that's really nice because this is a union, and that's also described as a union, right? Means the same thing. Let me talk about relative difference first, and then we'll go back and we'll draw the pictures for these. Relative difference is the set of all elements that's in one set that are not in the other. Okay, so this looks like, I meant to do black. It looks like it's subtraction. I don't know why I'm writing x. A minus B, that's what I want. So this is the set of all x, such that x is in A and x is not in B. So one way to think about this is, we can go back to our union idea. It's what you're bringing into that union and that marriage, right? Did you bring in the debt? Did you bring in the house? Did you bring in the child or the dog, right? That stuff you brought in to the situation, that is the relative difference. It's what your contribution to the situation is. It's often, there's actually a legal document that talks about this in this way. They don't use this words, but it's called a prenup. Have you heard of a prenup before? Right? It says that whatever you brought in when you leave, you take that with you when you leave. Right? It's based on this idea. Okay? A prenup idea. So let's take some pictures of, not take some pictures, but draw some pictures of these as well. So we have a Venn diagram for each one of these. I'm going to make these a little bit smaller so it has a little bit more space. And we're going to draw those overlapping circles that we were talking about before. Okay? So we're going to draw circles like this, not like that. Let's try again. It's a little bit better. And I'll draw the same circles in a minute on the next slide. Okay, so it's a basic Venn diagram picture where there's two sets. Okay, this is the very most basic one. And when we're looking at these, we're going to label them not like that. Oh my goodness. Touching too many buttons. A and B. Here we go. And what we're going to do is we're going to draw, oh my goodness. Keep my hands off the screen before I delete the whole thing. We're going to draw what is meant by the picture that's being described here. So it says the intersection on the first one, right? The intersection is what's common to both. What would that be in this picture? It'd be the middle. Yes, it's the part that's in the middle right here. Kind of that football shape there. Right, it's the overlap. It's what they have in common. A union is supposed to get everything in either set. What would that be in this diagram? All of the stuff in the circles. So it's everything in circle A, and then also the stuff tagged on in circle B. Right? It's the family picture. You get everything. And then on this one, relative difference, it's the things that are in A that are not in B. Where would that be? Yeah, the outside part of circle A, right? Not the middle, not the other piece. It's just the outer side of the circle. And in particular, the reason it's A and not B is because this says it's in A. Right? I could do B the relative difference of B minus A. So like A minus B looks like this. But if I did B minus A, I'd be shading in this piece over here where the circle B is. Tessa.
Can you go back?
Mm-hmm. Got it? Okay. Ready, guys, to do an example? All right, we're going to do an example that doesn't have a diagram necessarily associated with it. You can draw it within a diagram if it's helpful to you. But we're going to do this with some context. And it is a blended family kind of context situation because it works really well for these descriptions. Consider Mary, single mom to one child, Mark and Joe. And Joe, single dad to two children. Got to read those commas in there. Joe, single dad to two children, Jack and Jill. Mary and Joe get married, and together they have two children, Anne and Andy. If M is Mary's kids and J is Joe's kids, find and describe the following. All right. M is Mary's kids, J is Joe's kids. What would M intersect J be? It'd be Anne and Andy. And the context in which we're describing this is like, biologically related, what's written on the birth certificate, something like that. Okay, we'll go with that. I realize that that's not how family dynamics necessarily work. We're just doing this as an example, so don't take offense. What's the description here? What did you do to figure out what Anne and Andy? Why was it them? Yeah. This is the kids. We'll call it share, right? Or the kids they had together, right? The kids that joined them after they got married. Whatever description you want, those are all good ones. What would M union J be? Maybe all the kids, right? So in this case, it would be who? We got Mark. I think he was the first one listed, right? It's the family picture, yeah? It's all the kids. What would M minus J be? Maybe Josh's mark. It's the kids who, will use the word loosely, but we'll say belong to Mary, but not, what's his name, Joe? Okay. Or you could think of it as the kids that Mary brought into the marriage, right? The ones that came in with her when she got married to Joe. That would be fine too. Does that make sense? Got that family picture thing going on here. Okay, cool. So we're going to take a look at some properties of these sets and intersections. So in particular, the first one is commutative. This works for all sets A and B. And what it tells us is that if we do the union of A and B, it's the same as the union, of B and A. And if we do the intersection of A and B, it's the same as the intersection of B and A. Now, that's not saying the unions and intersections are the same, right? It's just saying that the order doesn't matter. If I had done on the previous problem every one of these, well, the first two anyway with the union and intersection, where I put Joe in front of Mary, right? Joe intersect Mary, or Joe intersect union with Mary, right? Either of those. All of the description, everything else would have been the exact same. The order doesn't make any difference. That's what the commutative property talks about, the order of something not making any difference. And we'll talk about this more when we get to chapter 3, but you use the commutative property all the time. And you will teach the commutative property, maybe not with sets, but you're going to teach the commutative property with numbers. Because every one of you is going to teach some child that 1 plus 2 is the same as 2 plus 1. You are. And in fact, that's a really good thing because it makes your addition facts a whole lot easier if you don't have to remember what order you're going in, right? Absolutely. All right, so that's commutative. Associative is the next one. Again, this is true for all sets, but we're going to need 3 of them now, so A, B, and C. And it looks like the following. If we do the intersection of A and B with the intersection of C, I could have done the intersection of B and C first and then intersected it with A. And the same is true for unions. So A union B union C is A union B union C. Okay, associative property is a grouping property. It's the same thing we mean when we talk about the word associate. Who do you associate with? Who's your friend group, right? So the associative property is a grouping property. It groups things together, and this says if I group them, I can do them in any order. I can change the groupings and I end up with the same thing as I had before. And then the last one, which is on your next page, is the distributive property. I know there's one more after this, but this is something different. The distributive property is the last set property. The distributive property is, again, for all sets A, B, and C. And it says what happens when we combine these unions and intersections into a same statement. That A intersect B union C is the same as A intersect B union with A intersect C. And you've seen this property before. We use it with whole numbers, right? Addition and multiplication, like multiplication distributing over addition, or multiplication distributing over subtraction. So it's the same kind of property. This is called the distributive property. All right, we have one more formula before we do an example, and we will have time to do both the formula and at least one example. Cardinal number formula. The cardinal number formula talks about a relationship between how many objects get counted when we do unions versus intersections. Right? So like when we did a union of Mary and Joe's kids, we got all 5 kids. When we did the intersection, we only got 2. We got a much smaller group, right? Intersections are smaller than unions. So this one talks about how those numbers are related. So if you're looking for the union, if you're looking for the cardinal number, which is the number of elements in the union, this is the same as finding the number of elements in one set, the number of elements in the other set, and then subtracting the number in the intersection. So I'm going to show it to you in 2 ways to justify why this should make sense. First, I'm going to do a Venn diagram. Then we're going to go back to Mary and Joe's kids so that you can see why that works over there as well. Okay? So if we do this with a Venn diagram, draw that same basic picture that we had before with our circles in it. We have A and we have B. Now, if we were counting all of the objects, the items, the elements inside of A, it would be all of this red. Agreed? And if we count up all of the objects inside of circle B, it's all of this right here. But do you see that some of those objects got counted twice? Yep. Some of them got shaded twice, right? So if I counted it when I counted the red shading, and I counted it when I counted the blue shading, I counted it twice. So this piece at the end is telling you that you need to remove the double counting. Well, the double counting is exactly the intersection. That's why it gets subtracted off. So look back at Mary and Joe. If I were to count the number of items here in Joe's set, I'm sorry, not Joe, in the intersection, there's 5, right? This is 5. The number here of M and union J is 5. We didn't actually write them out, but what is the number of Mary's kids? Should be 3. She had Mark and then Ann and Andy. What is the number of Joe's kids? More. He had 4. He had Jack and Jill, Ann and Andy. And what is the number in their intersection? 2, Ann and Andy. So check it out. If I take 3 plus 4, what will I get? 7. Why did I get 7? Because Ann and Andy got counted twice. So when I subtract out the intersection of Ann and Andy, it removes that double counting to leave me with the 5 kids, counting 1 per kid instead of counting Ann and Andy twice. All right, so let me show you one example before we leave, and then the rest will be posted online. Is that what I want to do? Now let me talk about Cartesian product first, I guess. Maybe we won't do an example. The examples will all be posted online. The Cartesian product is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. And it looks like this. Whoops. It's the set of all elements AB such that A is an element of A and B is an element of B. And we'll do this one and we'll stop. So if I had set A, and let's say that set A is X, Y, and Z. Okay? Those are the 3 elements that happen to be in set A. And set B is a grouping of numbers, 1 and 2. Doesn't matter what I pick, but it'll work. Then what happens when I do the Cartesian product is that I make ordered pairs. So I take an element from A and I group it with an element from B, X1. I can also take an element X and I could group it with the number 2. This is all one-to-one correspondences, which should sound like something we've done before, right? And then we can do this with Y. Y could be grouped with 1. Y could be grouped with 2. Or Z. Z can group with 1. Z can group with 2. Now, elements of the Cartesian product are ordered pairs. But I'd like for you to notice what happens, and I'll even change color to do it. If I count my one that I just did, these things, there is a relationship that shows up. How many items are in A? How many elements? 3. It's X, Y, and Z. How many elements are in B? 2. It's the numbers 1 and 2. How many elements are in the Cartesian product? 6. There are 6 ordered pairs, right? What would you conjecture is the relationship between these numbers? They're multiplied, right? The number of items in set A times the number of items in set P is the number of items in the Cartesian product. Right? 2 times 3 is 6. That is the relationship that's showing up here. Whoops. I'm going to write this down as our last thing. It is a true fact that the number of items in the Cartesian product is the number of items in each individual set multiplied. Now, note, if somebody tells you to find the Cartesian product, you're finding a list of elements like this. If somebody asks you what is the number of items in the Cartesian product, you're finding a single number like 6. Those are different questions. In of something means number. Without the in, they're not asking you to count things. They're asking you for the actual objects, the actual elements. Okay? We'll stop there for today.